Hello everyone. Today's lecture we will be studying relation. Relationship between elements of sets are represented using the structure called relation. Relationship between a program and its variable pair of city is linked by airline flights in a network. Basically in real life, the relationship between any two objects are called relation. In the same way, if there are multiple elements in a set and there exists a relationship between a pair of set, and that is called a relation. The most direct way to express a relationship between elements of two sets is to use ordered pair. For this reason, sets of ordered pair are called binary relations. As we have already discussed about the ordered pair, you can refer to the previous video. Let A and B be sets. We have two sets named A and B. The binary relationship from A to B is a subset of R of A Cartesian product B. A cross B is the sign of Cartesian product. Cartesian product is basically, it is not the multiplication, but it is the pairing of every element of A with every element of B. And when we perform a Cartesian product between A and B, we get all the possible pairs that may exist in real world. But the relationship, it's not essential that that the Cartesian product and the relationship are always same. Relation could be a subset of the whole Cartesian product. That's what the definition says. Where AB is a pair in the relation where A belongs to A and B belongs to B. In other words, for a relation R, we have R is a subset of A cross B. We use the notation ARB to denote that AB belongs to a relation R, and ARB bar notation to denote that AB does not belong to R. Suppose you have two sets A and B and you have performed a Cartesian product. Cartesian product basically means that every element of A will make a pair with every element of B. But the relation between all the pair is not possible. So relation is basically a part or a subset of the Cartesian product. So in this way, if you have to represent that a particular pair belongs to relation, then you have to write like this. And if you want to represent that from the Cartesian product, this set does not belong to the relation, then you have to write down like this. When A, B belongs to R, we can say that A is related to B by the relation R. You can see this example. In this example, let A be the set of student and B be the set of course. There is a relation between student and the course. Let R be the relation that consists of those pairs AB where A belongs to A, small a belongs to A and B belongs to B. Here the example says that we have a set A that contain all the students and we have a set B that contain all the courses. So the connection between these two are, if a student is enrolled to a particular course, then there exists a relation. See the example. If Jason is enrolled only in one course, that is CSE 20, and John is enrolled in two different courses, that is CSE 20 and CSE 21. That means Jason and CSE 20 are making a relation. John is making relation with CSE 20 as well as CSE 21. So you can write it as Jason and CSE 20, John with these two like this. And they all belong to a pair or they all belong to a set, or they all belong to a relation. But if there exists a pair like this, like Jason belongs to CSE 21, that does not belong to relation R, because the information that we have, according to that information, Jason has no connection with CSE 21. Let us consider another example, that is example 2. Let A be the student of CS major and B be the courses. These are the courses, these are the student name. We specify relation R is equal to A Cartesian product B as the set that lists all the students A belongs to A enrolled in class B belongs to B. See the relation R. This is the relation that specifies that which student is belong to which course. And what is the way in which you can represent a relationship? You can use a graphical representation or you can use a tabular representation. If talking about a graphical representation, this is the representation of this set. This is the set representation. We are representing relation in the form of set, and same is represented in the form of a graph and in the form of table. This graph shows if a student is linked to a particular course, then there exists a link. If this and this table represent that if this and this having a relation, then you have to mark a cross. If this and this not having a relation, then you can leave. For example, Alice is having a relation with CSE10, so that is why we have marked a cross. But Bob is not. Bob is not connected to CSE10. That's why I have left it. Next, this example. This example is showing that R is a subset of A cross B. How is a subset? How it is a subset of A cross B? We have given two set A and B. Then we have given some relation R. That relation is 0 belongs to A, 0 belongs to B, 1 belongs to A, 2 belongs to B. This is a relation representation. The Cartesian product representation is A belongs to this, 0 belongs to A, 0 belongs to B, 1 belongs to A, 1 belongs to B, 2 belongs to A, 2 belongs to B. This is the Cartesian product representation. I mean this. The relation that is given is only a part of that relation, and that is what mentioned here. Functions as relations. You might remember that a function f from a set A to a set B assigned a unique element of B to each element of A. A graph of f is the set of ordered pair A, B such that B is equal to function of A. Since the graph of f is a subset of A cross B, it is a relation from A to B. Moreover, for each element A of A, there is exactly one ordered pair in the graph that has A as its first element. If R is a relation from A to B such that every element in A is the first element of exactly one ordered pair of R, then a function can be defined with R as its graph. This is done by assigning to an element A belongs to A the unique elements B belongs to B such that AB belongs to R. Now we will be considering the relation on a set. A relation on a set A is a relation from A to A. In another word, a relation on a set A is a subset of A cross A. For example, let's consider this set A which ordered pair are in a relation A, B, where A is less than B. Relation on a set. Solution. See, how many relations are there? We have two sets A and A. This is A, this is also A. So, if you are talking about the relation that may exist, so the relation that is given is 1 belongs to 2, 1 belongs to 3, 1 belongs to 4, 2 belongs to 3, 2 belongs to 4, 3 belongs to 4. This is the set representation of the relation. This is the graphical representation of the same relation. And this is the tabular representation where if there is a pair, you have to mark a cross. If there Let A be the set 1, 2, 3, 4, 5 which ordered pair are in a relation R. AB, A divides B. This is the condition for the relation, and using this condition you have to find out the relation. So we'll get these set 1, 1, 1, 2, 1, 3, 1, 4, 2, 2, 2, 2, 4, 3, 3 and 4, 4. How many relations are there on a set with n elements? If you are having n element in a set, then how many relations can you form out of that set? A relation on a set A is a subset of A cross A. Whenever we find a relation, we have to perform A cross A. And if A has n number of elements, then A cross A will have n square elements. Therefore, we can have 2 to the power n square number of relations from any given set A cross A. This is the example. There are various properties of a relation: reflexivity, irreflexivity, symmetry, antisymmetry, asymmetry, and transitivity. Reflexivity: in some relations, an element is always related to itself. Let R be a relation on a set of all people considering of pairs x, y, where x and y have the same mother and the same father, then X relation X for every person X. Whenever a element, reflexivity means reflection or a mirror image, when an element is similar to itself or self loop, then it is called reflexive relation. Like 1 1 is reflexive relation, 2 2, 3 3, all these are reflexive relations. A relation R on a set A is called reflexive if A belongs to R for every element A belongs to A. If there exists any such element in the set, then that is called a reflexive relation. Let us consider the example of reflexive relations and the example of non-reflexive relations. And this is the given example, and you have to find out the set or the set of the relation where the given relation is a reflexive relation and where the relation is not a reflexive relation. So it is from the previous example. So this is not a reflexive relation. This is also not a reflexive relation. This is a reflexive relation. This is not a reflexive relation. This is also not a reflexive relation. Why? Let us see from the given example. Consider the point relation on 1, 2, 3, 4, 5. So these are the given relation. R1 is this, R2 is this, R3 is this, R4 is this, R5 is this, R6 is this. This is the example you have to do. R3 and R5 are both reflexive. Why? Both contain all the pair of the form 1, 1, 1, 2, 3, 3 and 4, 4. You have to consider all the possible pairs. I will try to see. In this example, we have 4 elements. So, any set that consists of all 1, 1, 2, 2, 3, 3 and 4, 4 will be the correct answer. So, look at this. This consists of 1, 1, this consists of 2, 2, this consists of 3, 3 and 4, 4. That is why it is the correct answer. It could contain any other element, but it has to contain all the reflexive pair. Achha, why not this? Because it has 1 1, it has 3 3, it has 4 4. It doesn't have 2 2. So this is the wrong answer. And why not this? Because it has 1 1, it has 2 2, it has 3 3, but it doesn't contain 4 4. That is it. That is why it is the wrong answer. Now, if this is clear, you can find out the correct pair. We have 4 elements. So you have to find out all the possible set where 1, 1, 2, 2, 3, 3, 4, 4 are all present. And if we consider this, we'll get only 2 sets, and those sets are R3 and R5. See, R3 and R5. And that is why they are called reflexive relations, then all the other relations are called non-reflexive relations. This is also an example. Let A is equal to 1, 2, 3, 4, 5 and define the relation R, the given. And you have to find out the reflexive and non-reflexive. R1 is reflexive. Why? Because it has all the possible pair of 1, 1, 2, 2, 3, 3 and 4, 4. R2 is non-reflexive because it doesn't contain 4, 4. Like this you can see. Now, the directed graph of a reflexive relation. If given a reflexive relation, how you can draw a graph? The directed graph of every reflexive relation include an array from every point to the point itself. Means it consists of a loop. Loop means A belongs to A, B belongs to B, like this. See? Yeah, A belongs to A, B2 belongs to A. Like if you are presenting this, then you have a self loop is present. So whenever self loop is present, it is reflexive. Whenever the self loop is not present, it is not reflexive. See, just a 1 belongs to 1, 1 belongs to 2, 2 belongs to 1, 2 belongs to 2. So this is also reflexive as it contains all the pair. So you can represent it as tabular form, set or graph, whatever you want. Now this is your task. For each of these relations on set 1, 2, 3, 4, 5, you have to find out the correct answer, and the correct answer is B. Any find out? Matrix representation of a reflexive relation. Let A be this, and A is reflexive if and only if AI and AI belongs to R for every I 1, 2, 3, 4 n. Now it is given that if I have to present it in a matrix form, how can you present it? How can you say that it is reflexive? See, all the diagonal elements are marked. Now, irreflexive is the opposite of reflexive relation. Means you will not consider the mirror images. That is, then only it is irreflexive. See the definition. A relation is irreflexive if every element is non-related to itself, or irreflexive is the opposite of reflexive. And the same way, you have to leave all the reflexive element and consider all the irreflective elements. Now, moving on to symmetry. What is the meaning of symmetry? Symmetry is similar. Like AB is a relation. So BA is symmetry to AB. A relation R on a set A is called symmetry if BA belongs to R wherever AB belongs to R. See, BA, AB. So these are called symmetry. A relation R on a set A is called antisymmetry if BA is equal to B whenever AB belongs to R and B belongs to R. Means there exists AB, but these two are same. And this is 1, 1. This is also 1, 1. See, symmetric. A relation is symmetric if for every AB there exists a BA in the relation. Example है. These are the example, and we'll consider definition also. Antisymmetry. A relation is antisymmetry if for every AB belongs to R, then BA belongs to R is true only when A belongs to B. Antisymmetry is not the opposite of symmetry. For example, these are the example of antisymmetry. What is asymmetry? Asymmetry is the opposite. A relation is asymmetry if for every AB belongs to R, then BA not belongs to R. Means you have to leave its symmetry from the relation. See the example. Which of these relations are symmetric and which of these are not symmetric? Check the answer. So R2 and R3 are symmetric. R2 and R3 are symmetric. Why R2 and R3 are symmetric? Because In this lecture, we will be studying transitive relationships. A relation R on a set A is called transitive if whenever AB belongs to R and BC belongs to R, there also exists a set AC that belongs to R. Means if A belongs to B and B belongs to C, then A is also belongs to C. See, if A is less than B and B is less than C, then A is definitely less than C. If A is equal to B, B is equal to C, then A is equal to also C. These are called transitive relationship. If there exists a pair in this set, then the relation is said to be a transitive relation. In this, you have to find out all the possible pairs that are transitive in nature. So the answer is R4, R5 and R6 are transitive. And why so? R4, R5. The answer is R4, R5, R6 are transitive. R4, R5, R6 are transitive because if 2 1 belongs to 1, 3 1, 3 2, 4 1, 4 2, 4 3, these are all different. 1 1, 1 2 means there has to be a pair 1 3. Yes, there is. See, that is the reason. See the solution. This is the example of transitive relationship. So how can we draw a graph of this? This is how we can draw a graph. A belongs to A belongs to 2, 2 belongs to 3, then A also belongs to 1 also belongs to 3. This is your task. What is counting relation? How many different reflexive relation can be defined on a set A counting n elements? If given a set A with n elements, so how many relation can we define? We can define relation on any given set. Relation on R subset of A cross A where which contains n square element. Therefore, different relation on A can be generated by choosing different subset out of these n square elements. So there are two to the power n square elements. A reflexive relation, however, must contain the n elements A for every A belongs to A. Consequently, we can only choose among n square minus n minus 1 element to generate reflexive relations. So there are 2 to the power n minus 1 of them. What is the meaning of this? This is in this we are calculating the number of elements that we can choose our relationship from. If there is a reflexive relation, means in any matrix the reflexive relation only are the elements that lie in the diagonal. So if there are n elements in a matrix, so there are n diagonal elements. So only you have to choose between those n. You have to choose your relationship. This is the relationship summary. What is the combining relation? Relation are set and therefore we can apply the usual set operation on them. Now we are simply studying the type of operation that we can perform on our set, and same operation you can perform on relation also, like union, intersection, minus, all of them. They work same, or they also work like same. Given R1 and R2, you have to perform the union operation. What union operation perform? It combines the two sets, and if there are any common thing, it will write it down only once, like 1 1 was the common thing. What is the intersection mean? Intersection means extracting out the common thing. So this is the common thing, and this is same as the relation. As this relation is same as you perform the set. As sets are also relation are also part of sets only. What are the how you perform R1 minus R2? Means you have to perform R1 minus R2 or R2 minus R1. And there is another important way to combine relations. Let R be a relation from a set A to set B and B as a relation from B to set C. the composite of R and S is the relation consisting of ordered pair AC where A belongs to A, C belongs to C, and for which there exists an element B belongs to B such that AB belongs to R and BC belongs to S. We denote the composite of R and S by SR. In another word, if relation R contain a pair AB and relation S contain a pair BC, then this contain AC. This is the example. This is the example of combining relation. The definition says, by itself, let R be the relation on a set A. The power of Rn, n where n is 1, 2, 3, 4, 5 were defined as R1, R2, R3, R4 and so on. This is the example. This is the theorem. The relation R on a set A is transitive if and only if Rn is subset of R for all the positive integer n. Remember the definition of transitivity. If A belongs to B belongs to C, then A also belongs to C. This is the question. What are the n-ary? Like binary, what are the n-ary relationship? A binary relationship involves two. N-ary means ternary means 3 and n-ary means there are multiple couples. Database and relationship. Let us take a look on the type of database, the relational data model. Consider relational database model has been developed for information processing. The database consists of records which are n-tupled made of fields. These are the major fields. So, this is an example of relation. Consider this. This is your task. You have to find out the primary key. Hello everyone. In today's lecture we will be discussing functions. Let A and B be non-empty set. A function f from A to B is an assignment of exactly one element of B to each element of A. This is how we represent a function. We write f function of A is equal to B if B is the unique element of set B assigned by the function f to the element of A. If f is a function from A to B, we write it as A belongs to B. Functions are sometimes also called mapping or transformation. Graphical representation. Functions are represented graphically in several ways. You can represent a function using a Venn diagram, or also you can represent a function using a graph, or you can represent a function using a plot. These are not function examples. Some function terminology. If A belongs to B and function of A is equal to B where small a belongs to A and small b belongs to B, then A is the domain of F, B is the codomain of F, B is the image of A under F and A is the pre-image of B under F. In general, B may have more than one pre-images. This is the example. This is the we have discussed in the previous example. This is the pre-image. This is the domain. This is the codomain. This is the image. Function visualization. This is the domain, pre-image, range, image, codomain, and a function A belongs to B has this relation in a visual form. Domain has a range under the codomain. Range versus codomain example. Suppose that f is a function mapping student in a class to the set of grades A, B, C, D, E. At this point, you know F's codomain is A, B, C, D, E and its range is unknown. Suppose the grades turn out all A's or all B's, then the range of F will be AB, but its codomain is still A, B, C, D, E. Function. Function, addition or multiplication. Let F1 and F2 be functions from A to R, then F1 plus F2 and F1, F2 are also functions from A to R defined for all x belongs to A by F1 plus F2 is equal to F1x plus F2x. The example is given. This is your task. You have to find the solution. One-to-one function. A function is one-to-one if each element of the codomain has a unique pre-range. A function f from a to b is called one-to-one if whenever fa is equal to fb, then a is equal to b. No element of b is the image of more than one element of a. Means every element of one element of a is associated to one element of b. In a one-to-one function given any y, there is only one x that can be paired with the given y. A function is said to be injective if it is one-to-one. This is the example of one-to-one example. A function is one-to-one if no more than one element in the domain is paired with the element in the range. See, exactly one element is paired to the exactly one element in both the domain. Note every uppercase number has exactly one lowercase partner. This is also an example of one-to-one relationship. A function that is not one-to-one is also given. Just consider left hand side and the right hand side. Only one element is associated from the left hand side to the right hand side, but in the second example there are two associations. That's why this is not an example of one-to-one. This is another example of one-to-one and not one-to-one. This is one-to-one as one is associated to one. This is not one-to-one because two elements are associated to one element. Exactly one is required. Example of one-to-one function. Fx is equal to x to the power cube. The cubic function possesses the property that each x value has one unique y that is not used by any other x element. This characteristic refers to one-to-one. For every value of x, there is a unique value of x cube. That is why this is a one-to-one example. Example of functions that are not one-to-one. Fx is equal to x square. Fx is equal to x square from the set of natural number n to n is a one-to-one function. Note that fx square is not one-to-one if it is from the set of integers negative, because negative minus 5 into 5 is also 25 plus 5 and 5 is also 25. This is not one-to-one relationship. That is why this is the example of not. This is your task. You have to if this equation x minus 2 is one-to-one or not, you have to tell me. Function one-to-one. A function is onto. Now onto function. A function is onto if each element in the codomain is the image of some pre-images. A function f a belongs to b is subjective या फिर onto if the image of f equals its range. A function f from a to b is called onto if for all b in b there is an a in a such that f is equal to b. All elements in B are used. A function is said to be subjective if it is onto function. An onto function. And this is not an onto function as these two are not associated to any. This is another example. 8 and 1 are not associated to anything. Not used. That's why this is onto function. Example of onto function. You can progress along the line. Every possible y value is used. This is also example of not onto function. You have to tell this answer to me. This is the graphical representation. Another function is bijective function. Function can be both one-to-one or on-to. A function f is one-to-one correspondence or a bijective or a reversible or invertible if it is both one-to-one and on-to. This is the example, both one-to-one and on-to, and all the elements are associated, that's why on-to. This is also one-to-one. This is neither one-to-one nor on-to. Same example, you can see. This is an example of bijective function. Example of functions that are not bijective. See for yourself. Now, inverse of a function. Given any function f, the inverse of the function f inverse is a relation that is formed by interchanging xy of x to yx of f inverse. The function g would be denoted by f inverse and read as f inverse. If you have given AB and you shift their position, and then that is called the inverse. Let f be defined as a set of values given by x if x values are given and y values are given. F inverse is simply, see, x become y and y become x. Both the position are shifted. This is the example. Function. Inverse of a function. Example देखिए. 1 4 is converted into 4 1. 3 6 into 6 3. 4 0 converted into 0 1. This is called domain. This is called range. And both the domain and range are shifted. How to find an inverse function? Write the original relation, switch x and y, add 4 to both sides, divide both by 2. This is the normal procedure that you can follow. This is another example, complex one. How to find inverse of power functions? This is the trick. You have to write down the original function and you have to switch xy, multiply both by 16, take both sides, 1 upon 5th power, simplify, and you can solve. This is also an example. Graph of a function. How to draw the graph of a given function. This you have already studied. If f is a given function, you have to plot it using. Now, what is the floor function? The floor function assigned to the real number x, the largest integer that is less than or equal to x. The value of the floor function x is denoted by this floor function, this floor symbol. This is the example, like 2.3, you will take 2 the floor, 2, 0.5, you will take the lowest. What is the ceiling function? Like ceiling function, it takes the uppercase. The ceiling function assigned to the real number x, the smallest integer that is greater than or equal to x. The same way, 0.3 will become 3, 2 become 2, 0.1 become 1, minus 2 become 3. These are the some useful properties of the floor and the ceiling function. You can just go through it. This is your task. You have to find out these numbers. Composition of functions. The composition of two functions g, a belongs to b, and f, b belongs to c, denoted by fg, is defined as this equation. This means that first function g is applied to the element a belongs to set a, mapping it onto an element b. The function f is applied to this element of b, mapping it on an element of c. Therefore, the composite function maps from a to c. These are the notations. Inside the function first, outside the function last. These are the certain examples. These are another examples. This is your task. Composition of function. Composition of function and its inverse. F inverse function x, f inverse fx is equal to x. The composition of function and its inverse is identify function ix equal to x. There are factorial functions also. The factorial functions n belongs to z denoted by fn is equal to n factorial. The value of fn is equal to n factorial is the product of the first n positive integers. Fn is equal to 1 to n minus 1 into n. These are the examples. Function of 1 is 1 factorial, of 2 is 2 factorial, 6 is 6 factorial. This is the exercise. Why if is f not a function from R to R if fx is equal to 1 upon x. You have to answer me this. Your exercise or assignment. All this. Perform the assignment.